Hi students, welcome to HD Labs. Now, today's article is another special article. We are going to begin with the article of the ray optics in the curriculum of the plus 2, term 2 syllabus. So the bigger topic is labeled as ray optics. Ray optics is a very big topic, very vast article. So it has two subparts, subtopics, which are labeled as the reflection of light and the refraction of light. We are going to begin the article with the refraction of light, and in that we are taking up a micro subtopic. So in the subtopic of the refraction of light, we are going to study today the refraction laws or the laws of the refraction and the opening introduction of the article of the refraction. The refraction, we all know, is a phenomena of the light. Now, when we are talking about the light, so the light directly isn't visible to us. You can take a torch with you and switch it on open, and you can see that in between you will not be able to see the light. But if it falls on your hands or it falls on the wall, you will be able to see the effect of light. And that effect of light can be via a reflection or a refraction or because of other phenomena like scattering of light or interference of light, polarization of light, many other phenomena like the dispersion of light. Right now, I'm going to talk about the phenomena which is going to be the refraction. And to bind the article of the refraction, we have certain laws. We're going to focus on today's session about the refraction laws. Have you seen your favorite pencil getting bended as seen by you and you got panicked? My pencil has got bended while it was dipped inside the water. But actually, when you take it out of the water, you find that your pencil is intact. Nothing happened to it. But you can see the twinkling of the stars, or you can have the duration of the day and night increased by roughly 2 minutes in the morning and the 2 minutes in the evening. All these phenomena are based upon the article of the refraction. You can jump into a swimming pool by observing this base of the swimming pool at a certain depth. But while you are inside the water, you come to know that actually the depth was more than the original. How you got fooled? Because we didn't know about the phenomena of the refraction. But we are going to learn about the phenomena such that we are actually able to see the phenomena and the objects and their images clearly. So we need to discuss about the refraction phenomena and the laws associated with this particular phenomena and talk about that what does a refraction actually does with a ray of light. That article you will be love to see, that is deviation of the light. Now, to have the refraction phenomena, we need to have at least two different mediums, different characterized mediums like air, glass, glass water, air water, or any two particular medium. So we need to classify the medium either as a rarer and denser. So we are going to check upon that how does a light is going to behave as it travels from the rarer to denser or vice versa from the denser to rarer. So let's begin the journey with the idea of the refraction of light. So what's the refraction of the light? Actually, whenever the light falls on an interface, what is an interface? The interface is supposed to be an imaginary boundary which actually separates the two medium. You can see that over here, there are the two colored mediums. Now, this imaginary boundary over here is known as an interface. Now, when the light is going to strike this particular interface, two kind of phenomena are going to happen simultaneously. When the light bounces back into the same medium, this phenomena is supposed to be known as what? Reflection of light. And when the light is going into the second medium, this phenomena is supposed to be known as a refraction of light. So it basically is a phenomena in which there is a division of the energy of the light. A part of the energy is coming back into the same medium and the part of the energy is going back into the another medium. Now, how do we exclusively say reflection and exclusively say refraction? When most of the light incident on the medium bounces back into the same medium. In that case, the phenomena is certified as a reflection, and when most of the light passes on to the second medium, in that case, the phenomena is labeled as a refraction. What we are able to see in both the cases, the light is deviating from its original path. Now, in the lower classes, we love to say that the light has bended. Of course, it has bended, as you can see. As you can see the bending of the pencil. But what we are going to learn today is the phenomena of the reflection or the refraction. Both actually does what? It actually deviates the light from its original path. Let's try to work upon this idea. So first of all, let's see what exactly happens when we are talking about two different set of media, rarer, denser, rarer. Now, the laws of the refraction suggest that when the light falls at the interface, so there is a point of incidence through which we are able to construct a normal. Let me write this as n cap. And then the law number 1 states that there is an incident ray and there is a refracted ray. So I have labeled them as incident and the refracted ray and the normal to the point of incidence all must lie in the same plane. This is labeled as a law number 1. Right? Repeating again, the incident ray, the refracted ray and the normal to the point of the incidence all must lie in the same plane. That's stated as a law number 1. And the law number 2 actually relates the angle with the normal. Let's say this particular angle is the angle of the incidence and this particular angle is the angle of the refraction. Now, both the angles labeled over there, see clearly, both the angles are measured with respect to the normal. And then we can relate them with their corresponding refractive indices. Let's say the refractive index over here is N1 and the refractive index over here is N2. So the law number 2, that's also labeled as Snell's law of refraction, says to us as the product of N with the sine of the angle with the normal is supposed to be constant. Now, how do I apply this? That is N1 into sine of phi. So what is angle I? The angle of incidence. And what is N1? The medium refractive index from where the ray is incident is equal to as N2 sine of R. What is angle R? This angle of the refraction. And what is N2? N2 is the refractive index of the medium in which we have the refracted ray. Now we are well versed with the laws of the refraction. So now let's understand what happens to the ray of light. In both the cases. Both the cases means if the ray of light travels from the rarer to denser, you can see that the light is deviating from its original path. Now this is the original path of the ray of light. I can write this as an incident ray. And what happens? There is a refracted ray over here. Because the ray of light has deviated from its path. And so I have the ray which is not passing through the original path. No, we actually know that there is a rectilinear or a straight line propagation of light. But with the help of the phenomena of the refraction, we are able to deviate the light from its path and the light is moving in this direction. I am mentioning this as a refracted ray. Now what I am able to see that there is a deviation produced over here. And this is measured as an angle of deviation. So what is the angle of deviation measured as? That's the angle contained between the incident and the refracted ray. We can also say the refracted ray to be emergent ray, and we can define the angle of the deviation as the angle between the incident and the emergent ray. Now see clearly that this angle is angle I and this angle is angle R. So this deviation angle is nothing but as angle I minus of angle R, because this complete angle was equal to angle I, subtracting from there angle R, so we get I minus R. So what is I minus R? That is the angle of the deviation, but you can see that the light is deviated clockwise. So you can write this as clockwise deviation. You can see in the next figure what is happening. The ray of light was originally moving in this particular direction. So that was the incident light. Had there been no boundary, no interface, light would have followed this particular path. But because of the boundary, there was a refraction. And so the light deviated from its path and started moving in this direction. So this direction is supposed to be the refracted ray. So what we are able to see that there has been a deviation produced over here. What's the value for the deviation? Since this is angle I and this complete is angle R, so we can say that this angle becomes equal to angle R minus of angle I. So the amount of the deviation produced becomes angle R minus of angle I, but you can see that the deviation this time is in the opposite direction, that is anti-clockwise direction. So do you feel that you have actually rotated the ray of light through clockwise or through anti-clockwise, and so we are basically controlling the path of the light. How we are able to do so? That is because of the idea of the refractive index. What is a refractive index? The refractive index primarily can be written as C upon V. What is C? C means the speed of the light in vacuum. Now we all know that the light travels fastest in the vacuum while it moves into any other medium. In that case, the speed of the light decreases. So let's say any material medium, we have the speed of the light in that particular medium given as equal to V. Now as we know that the C is always more than V. So this value is usually more than 1. Now we can also write it in a reverse mannerism that V is supposed to be equal to C by N. That automatically explains to me that suppose the value for the N is lower, in that case the V is going to be higher. And on the reverse note, of course, if I say that the value for the N is going to be higher, in that case the speed is going to be lower. So I'm going to demarcate between the medium. I can write that this is a rarer medium, which means that the refractive index is lower, so the speed is going to be higher. So the speed in the rarer medium is higher. In comparison, if the medium is supposed to be denser, and the speed is going to be lower. So the speed in the rarer medium is more than the speed in the denser medium. Now look at some examples of the practical conditions we encounter. When we talk about the air or the vacuum, we consider the refractive index for this to be as 1. If I consider for the case of the glass with respect to the air, so since the refractive index of the air is 1, so the refractive index of the glass with respect to air, that becomes as 3 by 2 standard. Otherwise, we have to look into the problem. Sometimes the value might be given as root 3 or maybe 1.73 or 1.7. It depends upon the composition of that particular glass. So this is a standard value just to explain to us that the glass is denser with respect to the air. Similarly, the most common medium which we get in the numericals is a water. Our eye has vitreous humor, aqueous humor as a liquids, and they are close to water, right? Why? Because the refractive index of the water is around 4 by 3, which is 1.33. And if you look into the refractive index of the liquid in your eyes, that is around 1.35, 1.37. So they are close to water. So our eardrops, so our drops which are coming from our tears are water. Is it so? Looks like so. So we have understood the refractive index and we have understood that the glass is denser than water. Why it is denser than water? Because the refractive index of the glass is more than the refractive index of the water. Now let's say the ray of light travels from the rarer to denser. So what happens? Let's apply the Snell's law. So the ray of light is coming from the rarer medium. So I'm writing this as NR. The angle of incidence is I is going into the denser medium, that is ND, and into sine of R. What do I find from here? I find from here is that a refractive index of the denser to the rarer medium, I am writing this equal to N, and which is definitely more than 1 because the denser medium has a higher refractive index. So I can write this particular relation as sine of I upon sine of R as equal to N, and this value is more than 1. Right, because nd upon nr is equal to n and n is more than 1, which explains to me that sine of I is more than sine of r. It explains that angle I is more than r, or the reverse, the angle r is less than angle I. So which means you can see from the diagram that angle r is coming less than angle I, so the ray of light is bending towards the normal, where this would have been the original path of this ray of light, but since the angle r is coming less than I, this complete angle was equal to angle I. But since angle r is coming less than angle I, so when a ray of light travels from rarer to denser, it bends towards the normal. Now, there is the reverse behavior of it also. So let's see the reverse behavior. If the ray of light travels from the denser to rarer, now the first medium is going to be the denser. So ND sine of I, it goes into the rarer medium. So that's NR sine of R. Now I can conveniently write that N is equal to sine of R upon sine of I. Now since N is more than 1, so I can easily comment that sine of R is more than sine of I, or angle R is more than angle I. So this time the angle of the refraction is more than the angle of incidence. So you can see from the diagram also that as a ray of light was supposed to travel, it was traveling from the denser to rarer. So this would have been the original path, but it has more angle R, so it deviated away from the normal. So what's the conclusion? If the ray of light travels from denser to rarer, in that case it bends away from the normal. Now these two conditions looks different. As we say that a rarer to denser bends towards the normal and denser to rarer bends away from the normal. But let me give you a very elusive idea over here. What I'm doing is I'm bringing a mirror in the path of the ray. Now that's a very interesting behavior. Now you can see that a ray of light is traveling from the rarer to denser. How does it behave? We know that we have already checked it, that it must behave bending towards the normal. Great, excellent. And now it falls on the mirror. And so by the principle of reversibility, it gets reversed. Angle I is 0, angle of reflection becomes 0. So the ray of light gets reversed. And now this ray of light moves along this particular path. Isn't it a beautiful phenomena? This particular principle is known as the principle of the reversibility, where the ray of light retraces its path if it is exactly reversed. So with the help of the mirror, we have exactly reversed the path and it is retracing it. But the more beautifulness in this article is, now if you see the red path of the ray of light, it is moving from denser to rarer, and you can see the phenomena that it is moving from denser to rarer, it is bending away from the normal. So in a single diagram, you are able to see that what is happening. The ray of light was moving from rarer to denser, bending towards the normal, and after the reflection, it is now moving from denser to rarer, and it is having a phenomena bending away from the normal. So this is what we wanted to learn about the laws of the refraction, the beautiful laws labeled as the Snell's law of the refraction, which is based upon the refractive index of the medium. One is denser, second is rarer, and based upon that we can talk about the deviation produced in the light. Hopefully you liked the article, you understood the article and got stronger in the concept. Thank you for watching.